Welcome to the video on Computer-Aided Drug Delivery System. This covers Unit 2, Part 1, and is presented by Dr. Krishna Yadav. This video introduces computational modeling of drug disposition. It provides a quantitative framework to predict and simulate ADME processes: absorption, distribution, metabolism, and excretion. These models use mathematical, statistical, and mechanistic approaches. Computational disposition offers several advantages. It aids in candidate optimization to improve pharmacokinetic properties early in discovery, supports dose selection, assists in human PK prediction using preclinical data, and reduces the burden of costly and time-consuming experimental studies. The modeling paradigm spectrum ranges from empirical to mechanistic approaches. This includes compartmental models, population PK, QSPKR, and PBPK models, each serving different purposes, from simplified clinical data reliance to detailed, physiologically based predictions. Computational modeling of drug disposition involves various ADME processes. Key areas include modeling drug absorption, distribution, excretion, and active transport, with sub-processes like solubility, intestinal permeation, and transporter actions. Our first topic is drug absorption modeling. Drug absorption is governed by the interplay of solubility, dissolution, permeability, and intestinal physiology. Accurate modeling of these factors is crucial for predicting oral bioavailability. The absorption funnel outlines comprise the three main stages of absorption. Stage 1 focuses on solubility, Stage 2 on dissolution, and Stage 3 on permeation. Each stage represents a critical step in the drug's journey through the intestinal epithelium. Solubility modeling predicts a drug's aqueous solubility, which is crucial for drug availability and central to the biopharmaceutics classification system. The principle is governed by thermodynamic balance, and models often use the Henderson-Hasselbalch equation for pH-dependent predictions. Solubility modeling can be classified into three types. Thermodynamic models are mechanistically rigorous. pH-dependent ionization models use Henderson-Hasselbalch relationships, and QSAR, machine learning models offer rapid screening using molecular descriptors. Comparing the models, thermodynamic models are rigorous but require solid-state data. pH-dependent models capture GI solubility profiles but miss supersaturation kinetics. QSAR/ML models offer rapid screening but extrapolate poorly to novel compounds. Advantages of solubility modeling include rapid in silico screening and accurate GI profile capture. Limitations include the need for solid-state data for some models and the extrapolation challenges of QSAR models. Solubility is critical for the BCS framework and formulation strategy. QSAR models leverage computational methods to predict physicochemical properties, like solubility, from molecular structures. The principles involve defining molecular descriptors, selecting algorithms such as regression or neural networks, and training models on diverse experimental solubility data. QSAR models offer advantages like rapid virtual screening, reduced cost and time, and insights for design optimization. However, limitations include the applicability domain, lack of mechanistic insight, and failure to account for complex solid-state effects. Dissolution modeling predicts the rate and extent of drug dispersion into solution. The Noyes-Whitney equation describes this process, relating the dissolution rate to surface area, saturation solubility, and the diffusion coefficient. This model is crucial for understanding how various factors affect dissolution speed. Dissolution modeling advantages include predicting in vivo profiles from in vitro data and supporting biowaivers. Limitations involve difficulty in capturing the complex GI environment and reliance on accurate input parameters. Dissolution is often the rate-limiting step for poorly soluble drugs, making its accurate modeling significant for formulation design and regulatory decisions. Next, we discuss intestinal permeation modeling, which computationally predicts drug transport across the intestinal epithelium. This process is a key determinant of oral absorption and bioavailability. Drug permeation involves multiple pathways. Passive transcellular diffusion is driven by concentration and lipophilicity. Paracellular transport is limited to small hydrophilic molecules. Carrier-mediated processes are parameterized using Michaelis-Menten kinetics. Permeation models include passive transcellular diffusion models based on physicochemical properties, paracellular transport models focused on tight junctions, and carrier-mediated transport models incorporating kinetics for influx and efflux. We also have PBPK absorption modules, such as ACAT and ADME. These models segment the gastrointestinal tract and integrate all transport mechanisms simultaneously, considering regional permeability and transit time. Advantages of these models include validated permeability estimates from CACO2 and PAMPA, integration of dissolution and transit in PBPK modules, prediction of regional absorption, and assessment of food and formulation effects. However, limitations exist. CACO2 models can overestimate efflux effects. Passive diffusion models struggle with highly polar or actively transported compounds. Tight junction permeability is hard to predict, and in vitro to in vivo extrapolation of transporter kinetics is a major uncertainty. When we're developing a new drug, one of the biggest questions we have to answer is, will it actually get from the gut into the bloodstream? To find out, we use the CACO2 permeability model, the industry standard for predicting human intestinal absorption. CACO2 cells are human adenocarcinoma cells that, when grown in a lab, organize themselves into a polarized monolayer. This mimics our own intestinal wall. It's a two-sided system. The apical side represents the gut interior, and the basolateral side represents the blood-facing side. These cells even form tight junctions to create a realistic physical barrier. This model is powerful because it captures two main types of movement: passive diffusion and active carrier-mediated transport. This is crucial because it shows us how drugs might be actively pulled in, or, just as importantly, pumped back out by the body. We quantify this using two key metrics. First is apparent permeability, or, which calculates the specific rate at which the drug crosses the cell layer. Second is the efflux ratio. By comparing the flow from the blood-facing side back to the gut-facing side, we can identify if the body is actively rejecting the drug. Generally, an efflux ratio greater than 2 is a clear indicator of active efflux. Now, while CACO2 is excellent for predicting the oral absorption of passively absorbed drugs, it isn't a perfect one-to-one replica. It often overestimates efflux because it has higher transporter expression than a native human intestine. It also lacks the mucus layer and the natural enzymatic activity found in a living person. Despite these limitations, the CACO2 model remains an essential, reliable tool for vetting drug candidates and ensuring they have the right profile to move forward in development. The CACO2 model principle involves measuring the apparent permeability coefficient, or PAP. The efflux ratio, ER, compares transport in both directions. An ER greater than 2 indicates significant active efflux. The protocol for CACO2 studies includes culturing cells to form a tight monolayer, and then applying the drug to either the apical or basolateral side. Permeability is measured over time to determine PAP and the efflux ratio. This illustration summarizes the CACO2 permeability model setup, showing the key steps for cell culture, drug application, and measurement of permeability and efflux ratios for drug transport studies. CACO2 models offer high throughput and good correlation for passive drugs. They are useful for studying transporter-mediated drug interactions and are a standardized, regulatory-accepted method. Limitations include over-prediction of efflux due to high transporter expression, limited applicability for paracellular transport, and the lack of a mucus layer and native enzymatic activity found in the human gut. While cell-based models like CACO2 give us a great look at biological complexity, sometimes we need to strip things down to the basics. That's where PAMPA comes in, the Parallel Artificial Membrane Permeability Assay. Unlike CACO2, PAMPA doesn't use living cells. Instead, it uses a phospholipid-impregnated artificial membrane to act as a barrier between a donor compartment and an acceptor compartment. Because there are no living components, PAMPA measures strictly passive transcellular diffusion. It's essentially a test of how well a drug can dissolve through a fatty layer by its own power. To quantify this, we calculate the effective permeability, or DOT. This formula accounts for the volume of the compartments, the surface area of the filter, and the time it takes for the drug concentration to reach equilibrium. We also track the % recovery to make sure we haven't lost too much of the compound to the filter or the equipment itself. The biggest advantage of PAMPA is its efficiency. It's highly cost-effective and can be fully automated, making it perfect for high-throughput screening, where we need to test thousands of compounds quickly to isolate their pure passive diffusion properties. However, that simplicity is also its main limitation. Because it's a non-cellular membrane, it lacks biological complexity. There are no enzymes, no mucus, and no tight junctions. It also can't account for paracellular pathways, the gaps between cells, which means it is highly sensitive to the specific chemical properties of the drug. In short, PAMPA is the quick-look tool of drug development. It's the best way to determine if a drug has the basic physical ability to cross a membrane before moving on to more complex biological testing. PAMPA uses a phospholipid-impregnated artificial membrane separating donor and acceptor compartments. Only lipophilic compounds diffuse passively. The effective permeability, PEF, is calculated based on the change in concentration over time. The PAMPA model predicts drug absorption by measuring how a drug moves from a donor chamber through a lipid-coated filter into an acceptor chamber to calculate its effective permeability, PEF. To ensure accuracy, we use the percent recovery formula. Percent recovery equals C_A asterisk V underscore A plus C underscore D asterisk V underscore D divided by asterisk 100. This equation acts as a mass balance, adding the drug found in the acceptor chamber, C_A asterisk V underscore A, to what remains in the donor chamber, C_D asterisk V underscore D, and dividing that total by the initial starting dose, C_0 asterisk V underscore D. By multiplying by 100, we get a percentage that corrects for membrane retention, identifying if any drug got trapped in the filter rather than passing through it. The PAMPA model offers a high-throughput, automated way to predict drug absorption by focusing specifically on passive diffusion, showing a high correlation with actual human oral absorption. However, its main limitation is that it lacks the biological complexity of real cells, meaning it cannot account for active transport, efflux mechanisms, or paracellular transport. Because it uses an artificial membrane, it may underestimate the permeability of compounds that rely on these biological pathways and is sensitive to the specific physicochemical properties of the lipids used. We now focus on PBPK absorption modules, specifically the ACAT model. The mass balance equation for the drug in each GI compartment is shown here. It accounts for drug transfer from the previous compartment, transit to the next, absorption, and degradation. While CACO2 and PAMPA look at the how of crossing a single membrane, the ACAT model, or the Advanced Compartmental Absorption and Transit model, looks at the where and when of the entire journey. In drug development, we can't treat the gastrointestinal tract as one long, uniform tube. The environment changes drastically from start to finish. The ACAT model reflects this by deconstructing the GI tract into distinct segments: the stomach, duodenum, jejunum, ileum, and colon. What makes this model so powerful is physiological integration. For every single one of these segments, the model factors in specific pH levels, fluid volumes, surface areas, and transit times. This is vital because a drug that dissolves perfectly in the acidic environment of the stomach might struggle in the neutral pH of the jejunum. If we look at the math, it's all about mass balance. The model tracks the rate of change for a drug in any given segment by calculating what's coming in from the previous segment, what's moving out to the next one, what's being absorbed into systemic circulation, and what might be degrading along the way. By summing up the absorption across all these segments, we get a dynamic picture of the total fraction absorbed, or, over time. The output gives us more than just a number. It simulates luminal drug concentrations at every stage. This provides the key insight researchers need. It identifies the specific rate-limiting steps. Is the drug's success limited by how fast it dissolves, or is it limited by its permeability? By integrating regional physiology with mathematical precision, the ACAT model allows us to predict human absorption with incredible accuracy, helping us fine-tune drug formulations long before they ever reach a patient. The ACAT model is a compartmental approach used in PBPK modeling to predict drug absorption in the GI tract. It uses a mass balance equation to track the amount of drug in any specific compartment over time. This calculation is the sum of the drug entering and leaving that section, factoring in the transit rate constant for movement between segments, the absorption rate constant for movement into the bloodstream, and the degradation rate constant for drug breakdown. To find the total amount of drug entering the body, we use the absorption rate equation. This is the sum of all individual absorption rates across every GI compartment, from the first to the last. By combining these equations, we can simulate exactly how much drug is absorbed into the systemic circulation over the entire length of the digestive system.
The ACAT model divides the GI tract into distinct compartments, like the stomach and ileum. It integrates physiological factors, such as pH and transit times, and drug properties, like solubility and permeation, to calculate the mass balance and absorption profile dynamically.
Advantages of ACAT include integrating in vitro, in silico, and in vivo data, and identifying rate-limiting steps for absorption. However, limitations involve the extensive input data required, sensitivity to input quality, and model complexity. Here are the references used for the content presented in this video. Please like, share, and subscribe.